Okay. We are recording. All right, so I'm going to take a look at chapter 14 really quick here. The review 14 hopefully is pretty, I think that's pretty straightforward. That's like probability stuff that you've most likely seen before. 14b, really like the big quick thing on 14b for these up here is they have to all add up to equal 1, right? Because that's the like total sum of the probability, and you can't have any negative probabilities because that doesn't make sense. You can't, you know, like if there's no chance of something happen, that's 0, but there's no such thing as a negative probability. So that one would not work just because of the negative already. Okay. Display the probability distribution. So with this, you're just making this graph here. All right, and then mode and median. Really quick, mode is the one that happens most often. So like if we're looking at this one, this is the mode 3. And then the median is to start adding up from the left. And then as soon as you get to 50%, that's your median class. So actually this one here, we're at 50% right between 2 and 3. So the median's at like between 2 and 3. That's a weird one. I usually try to make it so that it's really obvious. So like if we were doing, well, this one works here. So if we were doing this one, the mode is 1 and the median is 1 because it's already past 50%. Okay. So I'm trying to cover the stuff that I think is going to give you a little bit more trouble. I think that stuff should be pretty good. 14C. Let's see. I think Darren, weren't you saying that, like you want to help with like that the roulette question?
Yeah.
Okay. I think that this, because wasn't it like talking about the expected value or something like that? Is that? Good. Okay, let's try this because I think like this, is it 14C that you're working on?
Yeah, 14C part 2.
Yes. Okay, I think this is going to cover that too. So let's just try this one and then for certain I'll come and help you on that one specifically as well. But I think this might cover a lot of it. So in a carnival game, I'm just going to move it up so we've got more space here. A player randomly selects a slug from a bag of 18 slugs. If the player selects a white slug, they win nothing. If they select a red slug, they win $2. Blue slug, $5. Spotted slug, they win $10. There's 9 white, 4 red, 3 blue, and 2 spotted slugs. Create the probability of a player winning, calculate the probability of a player winning $10 in one game. So there are 18 different slugs to choose from. You only get to choose one. And then spotted slug is $10 and there's 2 of those. So we would simply just do 2 out of 18. And you can just leave it like that, that's fine. Or 1 out of 9. Or whatever the decimal is, which is I think 0.111 repeating. Any one of those is totally fine. Okay. Calculate the probability of a player winning at least $5 in one game. So that would be the 2 spotted slugs and the 3 blue slugs. So that would be 5 out of 18. Right. Or blah, 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 blah. And then let X be the money won from playing this game. Find the expected value of X. Now this is where it gets different, right? So what we want to do for 16 is we want to make really that table actually comes in really handy. If we do, let's see, we've got the win nothing, $2, $5, and $10, right? So we win nothing, $2, $5, $10. That's not 12, that's 2. Okay. Let's see. 9 of those slugs you're going to win nothing off of. 4 slugs you're going to win $2 off of. 3 slugs you're going to win $5 off of, and 2 slugs you're going to win $10 off of. So then what we want to do here, and again, normally this is going to show up as your table, right? You don't have to put it in the table. I'm just saying this is what is most likely going to be set up as looking like that. So what you want to do is just simply multiply these two numbers together. So 0 times 9 gives us 0. 2 times 4 gives us 8. 5 times 3 gives us 15. 10 times 2 gives us 20. And then we're going to add these all up. 8, let's see, it's 35, 43. Okay. So like for all 18 possibilities, if you were to like, go through and take time to play 18 times, and let's say if you chose exactly each one of those slugs, you would end up winning, like getting $43 back. But there's 18 total times that you play, right? So on average, the expected value of X is, there's 18 different ways to do this. So you take the 43, you multiply those all together, add them all up, that's 43 total dollars, but that's spread out over 18 games. So 43 divided by 18 gives us $2.39. That is the expected value. Is this here? Is this helping out? Is this making some sense? Okay. And this is kind of like that roulette one. That's why I wanted to hit this one. But so expected value is $2.39. So then question 17 says, if it costs $2 to play the game, what's the expected gain? So you're going to end up, for 17, you're going to end up winning $2.39 on average, but it costs you $2 every time to play the game. So your expected gain is 39 cents, which means every time you play the game, you should expect to win on average. So like you played 100 times, you'd win 39 cents on average every time. So 39 times 100, you win $39 if you played 100 times, right? So guess what kind of expected value every game in Las Vegas has? Any ideas what kind of value it's going to be? It's not always a specific value, but it's always going to end up being negative, meaning like that roulette question that you're talking about, you're going to end up you're going to end up on average losing, I think it's like about 5 cents every time you play or something like that. So it might be a little bit depending on how much. It's like a certain percentage, but anyway. Okay, hopefully that helps for this section, which was C. Oops. Good. And actually all this work here is also on the answer key. So if you want to see that, you can look back at that. Now, 14D, if 4 coins are tossed simultaneously, what's the probability of getting all this stuff here? So this is what, for like you guys in class, that's what's over on that board over there. We can do this a couple of different ways. We're going to go through and we can make this thing into a big, huge, like a tree diagram, right? And there's 4 coins, so we got to make 4 levels of this tree diagram. But I'm actually going to show you this, and then I'm going to show you how to use the binomial theorem, which sounds big and terrible and awful. But I'm going to show you how to do the binomial theorem, which is going to actually save you a lot of time. But I want to show you both ways. So first coin, we can either get heads or tails, right? And then on second coin, if you get heads on the first one, we can get heads on the second one, or we can get tails on the second one. And if you get tails on the first one, you can get heads or tails. It doesn't matter, right? You guys following what I'm doing here? Okay, so I'm just going to keep doing this, heads, tails.
Are you recording?
Yep.
Cool.
Yeah, so I'm going to post this afterwards. So this is the third coin. And then the last one, heads, tails, heads, tails. There is an easier way, but I wanted to show you this because this is the way. I mean, honestly, if I got this question before ever seeing this binomial theorem business, this is what I would do. I'm sorry, my tree diagram is, my branches are a little crooked here, but you get the idea. Heads, tails. Okay, so this is the 4th coin or the 4th toss, however you want to look at that. Okay. So it says, what's the probability of getting, say for 18, it's 3 heads and 1 tail in any order. So we got to figure out how many. I'm going to just do this. I'm down here. I'm just going to figure out how many heads total on, like, at the end of this branch. So 1, 2, 3, 4. There's 4 heads at the end of this branch. And then we'll assume that anything less than 4 is going to be, there's going to be some tails in there too, right? So this branch here is 3 heads and 1 tail. This branch here is 3 heads. Are you guys anyone not following what I'm doing here? Just counting the total number of heads that falls down to these branches. So like this branch here, we got tails, heads, tails, heads. So there's 2 heads. This one here, there's 2 heads, only 1 head there. 3 heads, 2 heads, 2 heads. You guys okay with this? Let's see. I'm hoping that your silence means yes, it's all good. Okay, there we go. So we have all that. Okay, so now this here says, what's the probability of getting, we'll do this in green, 3 heads and 1 tail in any order. So basically, it's all the ways we can get 3 heads, right? Which in this case here, there's 3 different ways. Now, nice part about this is that there's equal probability of getting heads or tails. So all of these are equal probabilities of getting down here. There's 16 total. So that means each one of these branches there's a 1/16th chance that they would happen, right? So on this case here, 3 heads and 1 tail in any order. 1, 2, 3, there's 4 out of the 16 total paths, which equals 25% chance that that would happen. All right. And then if we do 19, it says 2 heads and 2 tails in any order. So we just basically got to find all the 2s. So there's 1, 2, 3, 4, 5, 6 of those. So that's 6 out of 16, which is what, 3 8, which is 0.375, I believe. Okay, and then this one here is a little different because this one says 2 heads and then 2 tails. So we would just go 2 heads and then it would have to be 2 tails. There's only one way to do that. That is one of the 16 total ways, which let's see what that decimal is. Just making sense out there for anyone that's paying attention. You guys doing all right? Okay. Point. This is 0.0625. So like about 6% chance of that happening. At least 2 heads. So this is where we'd have to go through and figure out at least 2. So that would be 4, 3, 3, 2. It's pretty much anything except for 1s and 0s, right? So probably the easier way is to count all the 0s and 1s. There's 1, 2, 3, 4 1s and a 0. So there's 5 ways that you can't. So 16 minus 5 is 11 out of 16 chance. 11 divided by 16, 68.75. So 0.6875 chance on that one. And then at most 2 heads. So that would be, let's see, I've run out of colors. Let's do bright green. I think we can see that. There we go. At most 2 heads. So that would be all the 2s, 1s, and 0s, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's also 11 out of 16, which is 0.6875. Okay, now I know that was fairly long and kind of painful. There is a different way, and this is I kind of wanted to go through and show you this whole long way of doing this because we can also do this with what we call the binomial theorem. So this first one here. Now, here's what the binomial theorem does. You take 3 heads and 1 tail in any order. So basically, you just do this. We're going to say this is the probability of getting heads, and then this is the probability of getting tails. Probability of getting heads is 1/2. Probability of getting tails is also 1/2. And in this case right here for number 18, we want to get 3 heads and 1 tail. So we want to get, this is the probability of getting heads. We want 3 of those. So it's going to be 1/2 to the 3rd power. And then probability of getting tails is we want to get 1 tail. So we do 1/2 to the 1 power. Okay. And multiply those together. But now here's the part where this binomial theorem thing comes in really handy, is there's multiple ways of doing that. And without making this table here, we can actually do this, use this lovely thing called Pascal's triangle, which I'm going to put up here in the corner. Okay, I'll do that over here in black. Let's see. So we've got Pascal's triangle starts with 1s up here, and then you go down the diagonal each way with 1s. And then to find the numbers in between here, you just add the 2 numbers above it. 1 + 1 is 2. You do not have to memorize this. You can just write this down because you get to use your notes. So that'll be pretty easy to find this number here. 1 + 2 is 3. 2 + 1 is 3. 1 + 3 is 4. 3 + 3 is 6. 3 + 1 is 4. So this is the first row, second row, third row, fourth row. However many coins that we're tossing, in this case here 4 is what row we want to use. We want to use this 4th row here. Okay, now it's weird because you're tossing 4 coins, but there's 5 different numbers, so you're like, wait, that's weird. So here's how this works. This is 1 is the number of ways of getting 0 heads. There's 4 different ways to get 1 heads, 6 different ways to get 2 heads, 4 different ways to get 3 heads, and 1 different way to get 4 heads. So just basically always start with this first number here was going to be 0, and then just count up. Okay, so if you look at it, oh, let's see, there's 1 way to get 0 heads, and there it is right here. There's 4 ways to get 1, right? 1, 2, 3, 4 ones. So that's what this here is going to kind of help us take care of. So then when we go back over here, again, try to hang with me here. We're almost through this piece. And again, it really does get easier once you understand how to do it. But I wanted to explain everything in detail to make sure that you've got this. So on this one here, 18, we're doing 3 heads and 1 tail. How many ways can we get 3 heads? So I look underneath for the 3, and there are 4 ways to do that. So I'm going to multiply this thing here by 4. So if you do 4 times 1/2 to the 3rd times 1/2 to the 1st, that's going to give us, guess what? 0.25, which is the same as that right there. Okay. And then for 19, 2 heads and 2 tails. So again, I'm going to look just for, this is like this red here, this, we're going to consider this to be number of heads, just like what we did down here. Okay. These are the same thing. So with this here, sorry, we're doing 19, we got 2 heads and 2 tails. So how many ways are there to get 2 heads? There are 6 different ways. So we're going to do this. We're going to go 6 times 1/2. That's the way of getting heads, probability of getting heads, and probability of getting tails. How many do we want of each? We want 2 heads, so that's going to be to the second. And we want 2 tails, so that's going to be the second. You multiply that all out, and then you get 0.375, which is right there. Is this making a little bit of sense for those that hopefully you're staying with me here for a little bit, because this binomial theorem thing looks awful, but then once you understand how it works, it actually is such a big time saver.
I feel like we did this last year.
I'm pretty sure, let's see, it was not in the core topics curriculum for sure, but because I remember teaching all that, but if it looks familiar, that's great. That means you've seen it somewhere, so that's good. We do 20. This one's the 2 heads, 2 tails. So this is where it is kind of handy to have this here, but I'm not going to try to ask you any of those there. But
I mean, isn't it just 50?
What's that?
Shouldn't it just be 50
50 what?
as a chance?
Well, like getting heads and tails is going to be 50. Yeah, like each one is going to be 50. But this is saying getting 2 heads and then 2 tails. So it's probably get your first heads.
Oh, in order.
0.5. Yeah, right. It's all in order. So we lost our This is definitely not piano music anymore. Let's do George again. It's definitely oops. It's George Winston. Oh, nuts. Sorry, you guys. We gotta fix our music. It's kind of a harsh change to to go from piano music to Pearl Jam. Oh no, I don't want to play a song. I want to play a whole song. Oh, I had it. Oh. Let's just try this. I wonder if it'll let me play this. It'll say, okay, start a station. There we go. Okay. Went out. Okay, there it goes. Let's just go back to math. Sorry. Two heads, excuse me, 2 heads and then 2 tails. That's just our one. There's only one way to do that. That's our 1 out of 16. Now, this is the one spot where this binomial theorem is not terribly helpful. I'm going to try not to ask you that on the test, but then here's where it comes in really handy. At least 2 heads. 21. So this is where we'd want to go in with getting 2 heads and then 3 heads and then 4 heads. And we got to come up with all those probabilities and we want to add them together. So again, you can still do it with this. Where this comes in super handy is actually going to be the following sections, because like the probabilities aren't going to always be 0.5. When the probabilities start to change, then this becomes a lot more helpful than just a regular old tree diagram. Okay, so anyway, back here, probability of getting 2 heads and 2 tails. That's this one right here. So this I'm just going to transfer down into here. That's 6 times 1/2 squared times 1/2 squared, 0.375. Right, and then the probability of getting 3 heads we already did right here. So we bring that one down here. 4 times 1/2 3 heads, 1/2 1 head, 0.25. And then all we gotta just figure out the probability of getting 4 heads. So if we're gonna stick with this theory here, here's 4 heads. There's only one way to get that. So we do 1 times 1/2 to the 4th, and then 1/2 to the 0 gives us, I think that's our 0.0625. All right. Yep, that's that one. And then what we would do is add these all together. So 0.375, 0.25, 0.0625. Add these all up and we get some number 13.8. 0.6875 is the probability that you'll get at least 2 heads. Okay, and then at most 2 heads, what we could do, you could do it a couple different ways. We could go through and do the 0s, the 1s, and the 2s, add them all up. Or we can actually just figure out what's the probability of getting either, let's see, this was in gray green, of either getting 3 or 4, right? Because this is what you don't want. So if we add those 2 together, since we already did this, we do 0.25, 0.0625. So this is the probability of getting what we don't want. So that's 0.3125. So then you just find the complement of that. So we could do 1 minus 0.3125, which is going to give us, I'm just going to do a calculator to save us some time. 1 minus 0.3125 gives us 0.6875 probability, which is funny enough, it's the same as 21 and 22 actually have the same answer. Go figure. Okay. Yep. Okay. So again, I know that looks awful, but like you don't, when you go through and do this, I showed you this to show you how we would normally do it. And then I'm showing you now over here the shortcut. So you can officially do it either way. This way is going to take more time. Okay. Okay, 14E. Okay, so 20, let's see, 23. So what we want to do on this is where this little, this is where the calculator instructions come in handy. And that's this pink sheet. I gave you guys this pink sheet, didn't I? The little pink quarter sheet. Okay, so let's cruise through these really quick. And this will go a little bit faster. So I'm going to find, just so we have that here, let's see. I'm just going to copy one of these. Wow, that's big. Okay, so these, and then also for those out in those in the Zoom, this is, I put this here, I believe I put this, I'm gonna double check right after class, but I should have this in the Google Classroom. Yeah, this little binomial distribution piece here, so I'll double check just to make sure. Okay, so here's, by all means, use this, make your life easy. I don't need you to memorize this, but this was, I actually found this online. I felt this really was helpful for all this stuff here to figure out. So let's do this. There's a bag with 10 roly-poly bugs in it. 6 are female, the rest are male. So that would be 4 are male, right? 5 roly-poly bugs are chosen at random with replacement. Find the probability that exactly 2 are female. So if we use this down here, this one says exactly 2 are female. If you look here, there's like the little keywords in here. Look, exactly 1, at most, fewer than, more than, at least. When they use those words, this is what you're going to do over here. Okay, so and so yeah, we'll just use this piece. Okay, so first thing, n is the number of trials. So if you look on here, it says right here that 5 roly-poly bugs are chosen at random. So our n for all of these, our n is going to be 5. Probability of success, we're going to call that the probability of getting, say, the females. So that's going to be 0.6 for the females, for choosing a female roly-poly bug. And there are differences. I did look it up on the internet. There's differences between male and female roly-poly bugs. So anyway, and then X is going to be the number of successes. That's going to be the thing that changes here a little bit. Okay, so if we want to get we're choosing 5 roly-poly bugs and we want to get exactly 2, what we're going to want to do is pull up our handy dandy graphing calculator. And for those at home, I know Isaac, I know you have one. I'm not sure. Ariana, do you have a graphing calculator? Because if you do, that's going to make this a lot easier. If not, I'm going to find a way to make sure that you have one. I'm looking at your chat. You do. Okay, good. So you can like look right on here or whatever. So we're doing exactly 1. We're going to do this one right here. Okay, so really all we want to do with this here, and if any of you guys out there in class, you guys need one of these to follow along with, you guys good? I've got some back here if you want. So what we want to do this, we're going to do this. If you'll notice here, this top one here is the only one that does binomial PDF. All the rest of them are CDFs down here. So the only one you want to use this binomial PDF is if you are doing exactly 1. So we do second variables, which is distribution, I believe. Isn't that right? Yep, there it is. And we want to do on this first one, if we were trying to find an exact number, normal PDF. Okay, so we do normal PDF, and then it says X value, in this case here is our N. So we've got 5 trials, and your calculator might not look exactly like this. Is yours giving you this, or is it giving you something different? It's just giving you, it's just normal PDF, and it's got a parentheses, right?
Yeah.
So what you want to do is just put 5 in the first parenthesis, 5, just put 5 out of parentheses, and then put a comma, and then let's see. This here is our probability. Next one here is the probability of success. So we'll do 0.6. So on your calculator, you do 5, 0.6, and then how many number of successes do we want? On this example here, it was 5. So we're going to put 5 in here. So, but we want only 2. So we're going to do on the next one here, we'll put 2. And then here's where it's going to look the same as yours. So look, that's what yours should look like. Binom PDF 5, 0.6, 2, close it, push enter, and it's actually going to calculate that out for us. So the probability that exactly 2 are female is 0.0177. If I did that right, let's see, 23. I'm going to double. Oh, I got something different. Let's see, binom PDF 5.6 and 2. What did I do differently? Oh, because I did normal. Sorry, you guys, I did the wrong one. I got to go down. Sorry, that was, I totally forgot. Binomial PDF is down towards the bottom. Sorry, you guys. Binomial, because this is the binomial theorem. So binomial PDF, and now put in the same numbers. 5 trials, 0.6 is the probability that it's going to work. And we want to know what's the probability. Sorry, we want to know getting exactly 2. So we push that, then we get 0.2304. That's what we wanted. 0.2304. Did I go too fast for you on that one? We good? Yeah, okay. Good. Okay, so that's exactly 2. So again, now you don't have to make the T-chart. You don't even actually have to go through and do your, we could have done this with the Pascal's triangle and everything, but this actually will make this work without, so it's actually even faster than what we did in 14D. So 24, at least 2 are female. Let's do this in a different color. Let's do red here. So at least 2 are female. So look, I'm just going to go through in here and look, there it is. It says right there, at least, and I'm going to try to use these words here to make this really pretty straightforward. So we're going to want to do this. We're going to want to go into binomial CDF on this one. So second variables, go down to binomial CDF. I think it stands for combination of or something like that. I can't remember. So we're still going to do 5 trials. It's still going to have a probability of 0.6. And then here's where it gets a little weird. Okay, so to calculate the binomial probability of at least any number of successes. So like, let's say if we, in this example here, they always do successes equals 5. Okay, so they're saying if you want to get at least 5, then what we have to do is we're going to come up with the complement. This will help us find the complement. So we want to do, we're actually going to find the probability that X is less than 4. And that's what this binomial CDF does. It doesn't do at least, it does actually at most instead. That's how this works. So we just have to do this and do the complement. So if we want to know at least 2 are female, then we actually have to do 1 less than what we want. So it says at least 2. So you'll see here, they wanted to have 5 successes. So they took 1 away and put 4 in there. We want to have 2 successes, so we have to take away 1. So our X value is going to be 1. Push enter, enter. And then this is the complement of what we want. So we just have to do 1 minus that answer. And we get 0.912. And this was for 24, right? Yeah, there we go. Equals 0.91296, blah, 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 blah. Okay. Just making a little bit of sense, I hope. Are we almost out of here? So sad. Okay. 25, at most 2 are female. Okay, so if we're doing it at most, let's do this one here. At most, any number of successes. Actually, this makes it nice. At most 2 are female. So we're actually going to go through here. We're going to do second variables, binomial let's see, CDF, because that's what it says here. We're still at 5, still at 0.6. And then we want at most 2. So they had, their example was at most 5. Let's actually put a 5 in here. So we're going to put a 2 in there. And then it pastes it all in there. And that gives us a probability of 0.3174. You don't have to do you only have to do complement if you're doing more than or at least. Okay, so this is going to be 0.3174, so forth and so on. Okay. And then all are female. So I'm looking at that as, I think we could put that into, if you're picking 5, let's do this instead of all are female, I'm gonna do 5 are female. So that's exactly this. So that's back to this first one here. All right, so we could do second distribution. This is where we're gonna do the binomial PDF instead of the CDF. 5 trials, 0.6 chance of it being of them, the roly-poly bug being female, and we want to know what's the probability of all 5 happening. Piece that in there, and we get 0.7776. So about a 77% chance, 78% chance that they're all going to be female. Okay, and then let's do this one, and we'll call it good. Let's see, 27. First 3 are female, and then the last 2 are male. So this is one where you don't really need to use this one. I would just do like the exactly 2, at least 2, at most 2. Like these are going to be easier with this. But if this says here, it says the first 3 are female, and then the last 2 are male, we can just do this. What's the probability of getting a female? 0.6. And we're going to get 3 of those in a row. And then we're going to get 2 males in a row. Probability of getting a male is 0.4. And we want 2 of those. So what's the probability of that? We could just do multiply that all together, and then away we go. All right. So there we go. When we do that, let's see. So we can just do 0.6 to the 3rd. And then times 0.4 squared. And that gives us 0.03456. So about 3% chance that that would happen. Okay. Okay, I know I blabbed a bunch at you right there, but I really want to make sure that you guys got this. Okay, let's see, what's the only thing we didn't get? 15. 14F, mean standard deviation. Oh yeah, this one's a really pretty straightforward one if you look at the notes and stuff like that, but we can certainly take time later on to take a look at that. I see you. Hold on a second. I'm gonna just do this. I'm just gonna stop recording.